In this unit, we're going to learn about exponential functions and their inverse, the logarithmic functions. We're going to start by taking a look at graphs of exponentials. First of all, there is not one single parent function for exponentials. The base of the exponential, which is the number that is being raised to a power, can change. So depending on what the base is, the graph will look slightly different, but they'll all have the same shape, and they do have some other characteristics in common as well. So I'll talk about those as we get to graphing this particular parent function. We'll come back to domain and range after we take a look at the graph. The x-intercept we're also going to come back to after we have the graph, since we don't know how to solve an exponential equation yet. If we replace that y with 0, we have 0 equals 2 to the x power, and we don't have the tools yet in order to solve that. So we'll come back to that. We'll find the x-intercepts from the graph. The y-intercept we can find, replace that x with 0. Anything to the 0 power is 1. So the y-intercept is 0, 1. This is something that all exponential graphs have in common. Anything to the 0 power is 1. So any base to the 0 power will give you a y-intercept of 1. There is an asymptote, and we'll take a look at that after we see the graph as well. So let's find some other values. Raising 2 to the negative 2 power. Remember, a negative power means flip it and make the power positive. So we have 1 over 2 to the positive 2, which is 1/4. 2 to the negative 1 would be 1 over 2 to the first power, or 1/2. We already saw that 2 to the 0 power is 1. Of course, 2 to the first power is 2, and 2 squared is 4. We'll plot those points and see what happens with our graph. Negative 2, 1/4, negative 2, 1/2, 0, 1, 1, 2, and 2, 4. I'm going to plot a few more points just because I have room. 2 to the third power is 8. Graphing an exponential function, you can see this curve here. And thinking about what happened when we substituted negative values in for x, we had the reciprocal to the positive power. So we had 1 over 2, 1 over 4. The next we would have 1 over 8, 1 over 16, 1 over 32. So all of those numbers would be very small and approaching 0, but you would never actually get to 0 from a negative exponent. So that'll help us fill in our domain and range, as well as a few other characteristics of the graph. Domain for any exponential function, no matter what the base, is all real numbers. You can raise a number to a negative exponent, you can raise it to 0 as well as positive. From the graph, you can see that our graph is entirely above the x-axis, and as we talked about with those negative powers, we'll never actually hit 0. We'll get very small and very close to 0, but the value will never actually be 0. So we have a range y is greater than 0. In order to have an x-intercept, y has to equal 0. In this case, y never will equal 0, so we have no x-intercepts. Our asymptote is the line y equals 0. All 5 of these parts are consistent with any parent function, meaning as the base changes, the domain, range, x-intercepts, y-intercept, and asymptote will not change. The graph, again, will look slightly different, but it'll have that same basic shape. Next, we're going to take a look at graphing transformations of exponentials. Very similar to when we saw transformations of other parent functions. So you would have a value being multiplied out front, which would be a scale change. In this case, that would be a vertical stretch or compression. B is the base of the function, so that tells us which parent function we would use for our equation. C is a horizontal shift. It's grouped with the x. You won't always see parentheses. If it's in the exponent, it is with the x, so it would be opposite from the way that it looks. And then finally, we have our plus d, which is a vertical shift. Towards the bottom here, we also have some graphs. Depending on if you have a reflection, your graph could decrease. So our first example is like what we just saw. Our a was positive, greater than 0, and our b value was greater than 1, so we had an increasing graph. If a is positive, but your b value is between 0 and 1, your graph will decrease. If your a value is negative, that's a vertical reflection, your graph will decrease. And if your A value is negative, but your B value is between 0 and 1, your graph will be increasing. Our first translation, this is a vertical shift up 4, which will not impact the domain. The domain is all real numbers. Remember, if the parent function has a domain or range of all real numbers, no transformation will change that. However, when you shift the graph up, that does change the asymptote or the range in the same amount. So instead of y being greater than 0, we'll have y is greater than 4. Because we did not have a reflection, we're shifting our graph up. We still have no x-intercepts. Our y-intercept would be shifted up 4 as well. The y-intercept of our parent function was 1. When we shift that up 4, we would get a y-intercept of 5. If you're not quite sure how I got that, you can always substitute 0 for x and solve for y. 2 to the 0 power is 1. 1 plus 4 gives us that y-intercept of 5. Our asymptote would be shifted up 4 as well, so we would have y equals 4 for our horizontal asymptote on this one. Summing in those parent function values that we just saw in the first example, 1 over 4, 1 over 2, 1, 2, and 4. What we did in this case, we didn't change the x, but we had a vertical shift up 4. So we'll add 4 to all of those y values. Again, our x values stay the same, and our y values get added by 4. I have the parent function graphed for you so that we can see it in relation to our translation. I'm actually going to start by sketching my horizontal asymptote. Then we've got -2, 4 and 1/4, -1, 4 1/2, 0, 5, 1, 6, and 2, 8. So we can see the relationship between that parent function and the vertical shift up 4. This one we have a horizontal transformation. It looks like it's going left 3. We're actually going right 3. It's opposite of what we think. Domain, all real numbers. Range with a horizontal shift, it does not impact our range. We'll still have a range greater than 0. So the asymptote will be y equals 0 as well. X-intercept, still none. We will get x-intercepts if we have a reflection or a vertical shift down. Our y-intercept, shifting to the right 3, does impact that y-intercept a little bit. Let's substitute 0 for x and see what happens. We get 2 to the -3rd power. Remember, that negative exponent flips it to the denominator and makes it positive. So we have a y-intercept of 1/8. Subbing in those parent function values that we saw in the first example. This time our x value changes. We're going right 3, so we're going to add 3 to all of our x values, and we're going to leave our y values alone. Plotting those new points on our graph, we have 1, 1/4, 2, 1/2, 3, 1, 4, 2, and 5, 4. We also had our y-intercept at 0, 1/8, and that horizontal asymptote at y equals 0.